All right, so lesson 4. The first part of lesson 4 will be about something called Hooke's law, and then the second part of lesson 4 will be about elastic potential energy. So, first I want you to imagine that you have a mass attached to a horizontal spring. So maybe we have like a wall right here. And then this is some kind of horizontal surface, so it could be like a tabletop. And as long as this spring is not compressed or stretched, we would say it's at equilibrium. So if the mass was at rest and the spring was at rest and it was just in its natural resting state, then we would say that this diagram here shows the equilibrium position of the system. So here's another diagram where I'm going to try to explain what equilibrium is. So in the first diagram here, we have a spring that's just hanging there. This is its natural resting position. So we would say that this dotted line right here shows the equilibrium position of the spring. But now say somebody comes along and they hang a mass, so this red ball is a mass, on the end of the spring. That mass is going to stretch the spring. Now we have something called the displacement. So x is a variable, and it's the displacement. I know that we used a different symbol earlier in the course, but when we're talking about springs, we use x as the symbol. And x is always measured from the equilibrium position. So if you have a stretched spring, you can measure the x value for that spring by just measuring from equilibrium to wherever the spring is. Now there's one more case here that I'd like to draw in, and this is actually the case where the spring is compressed. So imagine now we have a situation where somebody pushes up on the spring from underneath. So the spring is going to look like this, is going to compress together, and we can draw another dotted line here. Okay, and this dotted line shows the compressed spring. And again, for compressed springs, we can measure x. X is always measured from equilibrium. So here, in the case of the compressed spring, this would be x. Okay, as soon as the spring is stretched or compressed, a restoring force tries to bring the spring back to equilibrium. And that restoring force, the symbol for it in this lesson is going to be F with an S, where the S stands for spring. And this is actually really similar to a pendulum. So the further the system or the spring is from equilibrium, the larger the restoring force will be. And the other thing to know about the restoring force is that it's always going to point towards equilibrium, because the restoring force is always trying to bring the system back to equilibrium. So this means that the more you compress or stretch a spring and the further from equilibrium that it gets, the more force you're going to need. And there's also something called the spring constant. So all springs have what's called a spring constant, which is given the letter K. The spring constant is a property of the spring itself. So different springs have different spring constants, and it's a measure of how stiff the spring is. So stiffer springs have higher K values. All right, so now we're going to try to put all of this together using a formula called Hooke's law. So Hooke's law is used when you want to calculate the restoring force acting on a spring. And right here, this part is Hooke's law in words. So let's break down what it says. So it says the force needed to extend or compress a spring. So the word extend is the same as the word stretch. This force is directly proportional, talk about what that means in a sec, to the spring's displacement from equilibrium. So remember, displacement is given the symbol x. Now, directly proportional means if x doubles, then the spring force also doubles. It means they copy each other. Or if x triples, the spring force also triples. or if X is 1/4 of its original amount, then the spring force is also going to be 1/4 of its original amount. And by the way, spring force and restoring force are the same thing here. So here's Hooke's law again, but this time it's written out using variables rather than words. And we actually need to add our vector symbols in here. So force is a vector, so is displacement. Let's add those into our notes. So the formula is spring force equals negative K times X. So we already talked about how K is the spring constant. Units for that are newtons per meter. We talked about how X is displacement and how it's always measured from the equilibrium point. And we're going to use meters for that one. And Fs is the restoring force, or sometimes called the spring force. And because it is a force, it's going to be measured in newtons, just like all other forces. All right, so please read example 1, pause the video, and then come back. So I've made a list of variables here. Now, because the formula that we're using has vectors in it, we need to write down our directions. So remember from the dynamics unit, we need to define our directions. So here, anything that is to the right, I'm going to make it positive, and anything that is to the left, I'm going to make it negative. Now we're going to draw a picture of what's happening here. So here, okay, we have a spring on a horizontal surface, and let's just draw the spring in equilibrium first. Okay, so here's where the spring is if it's in equilibrium. Now, let's draw where the spring is when its acceleration is 5.10 meters per second squared to the right. We need to think about this a little bit. So remember I had said earlier on in the lesson that the restoring force will always try to bring the system back to equilibrium. So if the acceleration is to the right, that means Fs is to the right as well. So when I draw my spring, the spring force acting on it has to be to the right. So what that means is this spring has to be compressed, because if I draw a free body diagram here, so if this is where the spring force is acting from, that spring force has to be pointing to the right, like this. If I had drawn this diagram instead, with a stretch spring, and then say this dotted line here is equilibrium, well then, looking at a point on the end of the spring force for this diagram that I just drew would be towards equilibrium, so towards the dotted line, and that arrow actually points left, not right. So I know that this diagram is wrong, and that this other one that I drew earlier is correct. So I'm just going to erase the wrong one because it's going to be in my way. So we have something like this. And remember, okay, that if we draw another dotted line, the distance between the two dotted lines is x. Okay, so let's see what we can do here. So let's draw a free body diagram for the spring when it is compressed. Okay, so because the spring is affected by gravity, we'll draw in the force of gravity. And then because the spring is sitting on a horizontal surface, the normal force is going to be directly up. Now, the normal force and the force of gravity are balanced forces here. They're the same number of newtons. And that's because although the spring is accelerating, it's only accelerating in the x direction. It's not accelerating in the y direction. So in the y direction, we have balanced forces. And then we already talked about how the spring force here is going to be to the right. Now, because normal and gravity are balanced and they're canceling each other out, the net force here is just equal to the spring force. So we can calculate F net by doing mass times acceleration. So let's do that. So the mass is 0.675 kilograms, and the acceleration is 5.1 to the right, but right is what I'm calling positive. So we'll make this positive 5.1. And when we do that, I get 3.4425 newtons. And this is going to be our spring force as well, because net force and spring force are equal. All right. Now we're almost done. Now we can use Hooke's law to actually solve the question. So Hooke's law says that the spring force is equal to negative K times X. So we can rearrange here for X, because X is what we're looking for. So moving the negative over to the other side and then dividing by K, we get negative Fs over K. All right, now we're gonna put a negative there because it's in the formula. And then in brackets, we're gonna write down Fs. Now Fs itself is a positive number because it's to the right. But the negative is still part of the formula, so we still have to include it. And then K is 9 newtons per meter. And when I do that, I get negative 0.3825 meters. And so putting this to 3 significant digits, I get 0.383 meters. And the negative means that it was to the left. So what's going on here is that it's just telling us that the location of our spring is to the left of the equilibrium position, right? So if you look over here, the spring is drawn left of equilibrium, which is this dotted line that I'm tracing over in red. All right, again, read example 2. All right, so for example 2, the difference here is that now this spring is being held vertically rather than horizontally. So that's gonna just change the free body diagram a little bit. The difference is that when you have a spring on a horizontal surface, Fg cancels out. And so you don't need to worry about the force of gravity. It's not gonna show up as part of the math. But for a vertical situation, you have to consider gravity, the force of gravity, because it's gonna actually affect your math. So if we draw this, okay, we're gonna have our spring, and when the spring is just hanging naturally, that's where it's gonna be. But then when somebody hangs a mass on the end of the spring is going to stretch out. Okay, so this first position that I drew, that's equilibrium. And then down here, this second position, this is where there's a mass attached to it now. This is where the spring is, and it's telling us that this distance here, this is X, this is 12.4 centimeters. Okay, let's draw a free body diagram for the spring at this moment in time here where I'm putting the star. Now, we're making an assumption here that the mass is at rest. Okay, so we've hung the mass on the end of the spring, it has stretched the spring, and then it has stopped and it's just hanging there. So this right now is at rest. Okay, so the free body diagram there is going to be the spring force is actually what's holding the mass up, and then the force of gravity is pulling everything down. So here spring force is acting kind of like a tension force. We're just not calling it tension, we're calling it spring force instead. And notice that the spring force is pointing towards equilibrium, right? At this point with the star here, if I draw towards equilibrium, I would be drawing up. Now, because the mass is at rest, and we learned in the dynamics unit that things at rest have balanced forces, that means we know the size of the spring force is equal to Fg. But we also know that Fg is equal to mg. So let's calculate that. So m is 2.45, it's given in the question, and g is 9.81. I'm not worrying about direction here yet, I'm just trying to get a number for the spring force. So I'm not really caring if 9.81 is positive or negative. And I do this and I get 24.0345 newtons. Okay, now I'm gonna manually put a direction on there. So just by looking at my free body diagram, I see that this is an upward force. Okay, so now for the final part of this, we're supposed to be finding the spring constant. So now we can use Hooke's law. Okay, so Fs is equal to negative Kx. When you are ready to use Hooke's law, you should define your directions. So I'm going to make up positive, and I'm going to make down negative. And I'm going to rearrange for K. So K is going to be negative Fs, if I move the negative over to the other side, and then divide by X. Okay, so we have negative, and then Fs is 24 up. So inside the brackets, we're going to have positive 24, because up is what I'm calling positive. And then for X, so we know that X is 12.4 centimeters, but we need to think about whether it's positive or negative. So look back at this diagram here that I'm going to circle in purple. And what you do is you look at your mass. So right here, outlining it in purple, we ask ourselves, is the mass above equilibrium or below equilibrium? And the mass is below equilibrium, so that means we had to move the mass down to put it down here. So since the mass was moved down, that's the same thing as saying that its x value is negative. So here we're going to plug in negative 12.4, but remember we don't want to work in centimeters, so actually we'll write 0.124 so that we can have it in meters. And then now our negatives cancel out there and we get 193.82 ... newtons over meters. And so to 3 significant digits, we get 194 newtons per meter.